Okay, today I want to so the where was so today today I'm going, but is it possible to move them, or it means that well, actually it's not so hard, so and it doesn't look like they will break. Okay, so uh, I'm, I'm continuing this story about spaces of conformal blocks. And now I'm adding another ingredient. So in principle, what we found. So if you have a Virasora, then such conformal blocks, one-point conformal blocks, form one-dimensional space for delta equal to 0, and zero-dimensional space for arbitrary delta. So this was one example. Then we had these two-point conformal blocks with delta and delta prime. When and we had that when delta equals to delta prime, dimension is equal to 1 when delta is different from delta prime. Dimension of the space is 0. And for 3-point conformal blocks with delta delta 1, delta 2, and delta 3. Dimension was 1 always. And when we switch to 4-point conformal blocks, maybe delta 0, delta t, delta 1, delta infinity, then dimension was infinite. And bases in the space of conformal blocks can be formed by such conformal blocks with fixed intermediate dimension. This is one basis. So it's for a generic situation, but we can consider the situation where one of these representations contains a null vector. So suppose that maybe let us put here 0, 1, and infinity. That some combination of C y L minus y acting on delta 1 is 0. L k greater than 1 acting on this gives 0. So it has vector for the Virasoro algebra. If this happens, we can ask for we can consider such representation that this vector is really 0. So so if you want to consider a unitary, for example, unitary representations, or at least even if the norm is not positive definite, we can ask all vectors of all vectors that are orthogonal to everything be 0. So
saying that such vectors are orthogonal to elements in the vector model.
Yes, because this is precisely what happens when we start to compute this. And yeah. So and if you ask for this, it means that if we substitute this vector in this trilinear functional, or in that functional, it should also be 0. So and let us see what it means. The simplest example is L minus 1 of delta 1 is 0. It means automatically that delta 1 is 0. And so we see that the correlator of such three operators of delta infinity, or maybe of infinity O delta 1 of Z O delta 0 of 0 equals to 0. Which means that this function is Z independent, and so it means that this operator O delta 1 of Z is just identity operator. is precisely the operator which is queued by a derivative or by L minus 1. And this three-point function turns into uh, and, turns into how to write that. Because of this, we have this equality that this three-point function is no. Well, let us say that 3-point reduces to 2-point. And when it happens, we see that since we are working with 2-point functions, now this situation is different. So when delta infinity is different from delta zero, we have zero-dimensional space of conformal blocks. When delta infinity equals to delta zero, we have one-dimensional space. Is it fine? So at this moment it's something very trivial. So, but let us move further, and so it was a null vector. They're also called singular vectors. So this was this highest vector on the first level, but we can also consider something on the second level. So we can say that there is some vector L minus 1 squared plus some coefficient times L minus 2 acting on delta 1 some kappa. It should equal so it should be highest vector of Versor. So L1 acting on this and L2 acting on this should be 0. So first we should find when such vectors appear. So and what is the analog of this condition? Delta 1 is 0. Like for which dimension can this happen? So the first equation that it is killed by L1 can be written as what L0 L minus 1 plus L minus 1 L0 plus kappa plus 3 kappa L minus 1 delta 1 is 0. And so second condition is one reactor is L2. It gives 2. No, I missed the factor of 2 here, and there. And here it will be a factor of 3. Will be 3 L1 L minus 1 plus 3 L minus 1 L1 plus 4 kappa L0 plus so it's 0 over 12 4 times 4 no 0 over 12 let me write 2 times 3 probably. Alright, n squared minus 1 times n delta 1. Fine. So
You commuted L1 and L-1 and so on and so forth.
yes, it's commutator with L minus 1 squared. This is commutator with L minus 2. This is commutator with
and then you use the fact that the positive coefficient they kill the.
Yes,
okay,
yes,
so.
of course. So now this and now we need to commute it once again here. And it will so it will be 4 L minus 1 L0 plus 2 L minus 1 plus 3 kappa L minus 1 epsilon delta 1 equals to 0. And second equation will be we need to compute this and it gives 6 L0 plus we can cancel this immediately because L1 is on height. Plus 4 kappa. So it would fine. It should be 4 kappa L0 plus C kappa over 2 times delta 1 equal to 0. So that's fine. Now, so let us look at this coefficient. It is for 2 plus it's 4 delta 1 plus 3 plus 2 plus 3 kappa equals to 0. And here it is 6 delta 1 plus 4 kappa delta 1 plus 3 kappa over 2 equals to 0. So you can express kappa from here. And substitute in this equation oh, I missed so it was C plus minus C delta 1 plus 1 over 3. So there is some equation which is not very nice. But, so it's some quadratic equation in this delta 1. And to solve this, probably I would like to introduce some convenient parameterization of C, and then we'll obtain it in some other way. Namely, this parameterization is C equals to 1 plus 6q squared when q equals b plus b inverse. Or maybe let us first just solve this as a quadratic equation and then use this parameterization. So let us first just solve this. So uh, we should multiply by minus 3 over 16 everything. Delta 1 squared something like this, right? So it is delta 1 squared plus delta 1 so this is maybe it's correct, right? Plus 1 over 16. So therefore delta 1 is equal to 5 minus c over 16 plus minus square root of 5 minus c over 16 squared minus 1 over 16. So let me check if this is still visible. Is no, maybe it's better to move to the other blackboard in this moment. So delta is equal to we can now factorize this expression as so right, just 1 over 16 square root of 5 minus c be minus 4 and plus 4.
I think that is kind of series here.
Where? Oh, this is why I'm thinking that something that it looks wrong because the branch points should be different. Thank you. And so it is also here. Yeah. So yeah. Thanks. So yes. So now it will be 25. Then minus minus uh, uh, 10 C. So on the sign is correct. Or minus 16 C plus C squared. Mm-hmm. Yeah, now it's much better. So this can be written as C minus 1 times C minus 25. And now, why is this parameterization nice? Because now C minus 1 is just so C can be written either as 1 plus 6 B plus B inverse squared, or it can be written equivalently if we rewrite it as square of difference. It can be written as 25 plus B minus B inverse squared. So this is parameterization of something which has branch points at 1 and 25. So this delta is written as and also it equals to to 7 no to 13 plus b squared plus b minus 2. Yeah. So and now we write it as hmm? Oh, so here we have 6 times 2. Yeah, yeah. So here we have this 8 plus b squared plus b inverse over 16 plus minus 1 over 16 and oh, I missed factor 6 here. So it will be 6 over 16 square root of b plus b inverse squared b minus b inverse squared. So it will equal uh, to 8 plus b squared plus b minus 2 over 16 plus C, and I put here 6 because it's a common factor of this. So here it is 3c over 8 b squared plus minus b squared minus b. Oh no, what's c? 6 over 16. 3 over 8 b squared minus b inverse squared. And then it equals to what? Maybe it's better to keep. Oh, wait, I've lost this factor of no, immediate. I've lost this factor of 6 here. So sorry. So it will be 8 plus 6 minus 2. So here it turns to 4 plus 3 b squared plus b minus 2 over 8. And here it is 3 over 8. And this one. So after all, if we take the plus sign, we get either 1/2 plus so it's for our upper sign 3b squared over 4, and for the lower sign we get 1/2 minus 3 b minus 2 over 4. So it's kind of expected that dimensions that B to B inverse maps one solution to another one, because central charge was symmetric, and B to B inverse.
But they put at the same sign?
Yes, thanks. So this is called delta 2 1, and this is called delta 1 2. So we see that this is the analog of this condition. Delta 1 equals to 0, and this 0 can be called delta 1 1. And let us also introduce another parameterization. So this was a parameterization for the central charge, and let us now introduce a parameterization for a dimension. Say that it is some charge alpha, and the dimension is given by alpha times q minus alpha. Q is b plus b inverse. And let us find alphas which correspond to these dimensions. Uh, uh, Namely, let us just compute delta of minus b over 2, just for curiosity. It is minus b over 2 times uh, so this Q is B inverse uh, plus 3B over uh, concerning the signs wait, did I make any mistake? Yes, I did, because here it was 5 minus C, and there should be a minus here. So sorry for all these mistakes. So minus here. So minus no, wait. It's overall minus, right? Because 13 minus 5 and yeah, it's overall minus. Sorry. So when we have upper sign is minus 1/2 minus 3 b minus 2 over 4, and here we have this one. So and this is called 1 2. This is called 2 1. Oh no, this bad. If the answer looks like correct, it does not necessarily mean that it is correct. Yes, now this one should be correct. So let us compute. Let us finish this computation. So this is 3b over 2, and this actually gives a minus 1/2 minus 3b squared over 4. So it equals to delta to 1. And in the same way, delta of b over 2 equals minus b inverse over 2 equals to delta 1 2. So and like for the future, let us maybe introduce the notion of alpha and m, which is 1 minus n over 2b plus 1 minus m over 2b inverse. Then delta and m is delta of alpha and m. So it's just a useful notation, but we'll see why it is useful. So for the moment, we just see that this equality holds. right? But let us now see what this means for the space of three-point conformal blocks. So we know that if we substitute here, if we substitute identity operator, then space of conformal blocks becomes either one-dimensional or zero-dimensional. Let us see what happens here. So, namely, we ask this correlator to be 0. By the way, we still need to compute this null vector, so we need to compute kappa. Kappa equals to minus 4 delta 1 plus 2 over 3. So for this delta 1, 2, like 1, 2, it is just b minus 2. And kappa to 1 is b squared. So so the equation is where was this?
Just to see if I understood the logic. So right now we don't care, like we suppose we have any possible primary in our spectrum, and we are looking for objects in like the first descendant, second descendant, third descendant, which are degenerate in this sense.
Yes.
Which like the Virasoro descendants, like at any step is not the full dimension that it should have. Because there is one which is not linear. The vectors are not linearly independent.
Yes. In principle, if you consider abstract Varma module, they will be linearly independent, but some linear combinations like this can turn out to be orthogonal to the whole Varma module. And in this case, we say that this vector should be put to 0, that may factorize over this submodule.
Okay, but I mean, in principle, like if I take CFT, I don't have an operator, a primary whose dimension is one of these two, right?
It depends on which CFT you have.
If you take random one, you won't have.
Yes.
Okay, so this is just an after consideration.
Yes.
So,
We are studying the spaces of conformal blocks, and actually it turns out that it is always useful to add such a degenerate field, especially 1, 2, and 2, 1, to no, to conformal blocks. Like if you want to study properties of generic four-point conformal block, it is useful to consider a 5-point conformal block with the insertion of such a primary field. Because as you will see, this lives almost in the same level of complexity of conformal block, but it works a kind of probe on the space of conformal blocks. For example, we can see we can compute monodromies of the degenerate fields and say something about the action of the monotomies of on the space of conformal blocks. We can diagonalize them and so on. Okay. So it is this statement. So we can check that maybe it was better to write a kappa inverse anyway. Kappa was in front of L2, L minus 2, right? So this is at L minus L minus 1 squared plus B inverse B minus 2 L minus 2 acting on delta which one? Maybe delta 1 2 is 0 and L minus 1 squared plus B squared L minus 2 delta 2 1 yeah. We'll actually need these equations with precise value of coefficients when we'll study Liouville theory and its classical limit, because it makes sense to study the limit when b goes to 0 or to infinity, which is the same. Okay, so we have this null vectors, and now let us compute their action on the 3-point correlator. So if you consider so where to write this? Probably I can start here. So let us start from 2 1 probably. Or just consider everything for 2 1. So we have the correlator with some over infinity O1 of point Z. We introduce this Z. O0 of 0. It equals to Z to delta infinity minus delta 1 minus delta 0. We know this. If I now insert here L minus L minus 1 squared, so O infinity L minus 1 squared acting on O1 of Z O0 O0, it will be a second derivative in Z, so it will equal to delta infinity minus delta 1 minus delta 0 times delta infinity minus delta 1 minus delta 0 minus 1 times Z to delta infinity minus delta 1 minus delta 0 minus 2. So the first computation. And now let us insert, oh, this one is easier. And now let us insert here L minus 2. It is the integral of of the Degenerate momentum tensor divided by z minus w around O1. So it is dw or w minus over 2 pi I w minus z around z. O infinity t of w O 0. So let us now move this to 0 and to infinity. So it is like this. So it is z, and this integral w goes in this direction to infinity, and in this direction to z at 0. So it is minus integral at 0, and let us expand this. W minus 0 and 0. And here we expand the energy momentum tensor. We write the OP with O0. So it is O infinity. There was actually O1. O1, 1, and sum of L k's over W k plus 2 acting on O0. One term plus another term, integral around infinity, W over 2 pi I, and here W is greater than Z, so this term is expanded in a different region, so it's 1 over W plus Z over W squared plus and so on. And here we have sum of L k's acting on O infinity over W L minus k's acting on O infinity over W. No, maybe better to write. Oh, it's fine. O1, O0. So now let us look for non-trivial terms. So when k equals to when k is negative, then these powers of W are positive, and they actually they don't give residue at 0. So the only meaningful terms are for k equals to 0 and k equals to minus 1, right? So Mm. So because k is greater than 0, then this vanishes. When k equals to -2, it's already regular. So we get here O infinity O1 of z, and maybe uh, maybe it's better to rewrite it as in this matrix element notation. So it will be delta infinity O1 of z L0 over z squared plus L minus 1 over z delta 0, this term, plus plus such term at infinity. So it is delta infinity. And here, again, let us see which terms are meaningful. So here, k is when k is wait. So when k is negative, then this else act by 0. When k is equal to 0 or to 1, then we can get something non-trivial. So when k equals to 0, it means no, maybe. Let me think. I'm always missing this. Maybe, well, to simplify things, let me maybe switch to this bracket notation at this stage. So it will be a sum of Lk's over Wk plus 2 acting on delta 0, delta infinity. And here it will be the same, delta infinity sum of Lk over Wk plus 2, because I didn't want all these conjugations and so on, O1 of z delta. So now it should be better. So now when k is equal to 0, no, maybe it's fine. When k equals to 0, it is nothing because it's W here when k is negative, then it then it vanishes because it is killed by negative else. And then there are options. No, maybe what I'm trying to maybe I forgot. Maybe there are just no non-trivial terms in this domain. So it's d squared. Well, the first non-trivial term should be for k equals to 2 minus 2, but it kills the state. Or probably, oh, maybe, but maybe the answer is that this term just does not give any contribution. Maybe that's all. So. And here maybe it's correct that only these two terms can contribute, right? Yeah. Yes. Sorry for being slow. So now we can compute. So this one acts by dimension, and this one should be moved on the left. So let us remember the commutation relation that L n was O equals to n plus 1 the n delta O plus the n plus 1 dO. So for so commutator with L minus 1 is just derivative. And this commutator is taken in the opposite direction. So it is delta 0 plus minus derivative in L minus 1, and we are differentiating this function. Minus delta infinity minus delta 1 minus delta 0. And all this is multiplied by z to delta infinity minus delta 1 minus delta 0. Right? Minus 2. So now let us do this for delta to 1. So our equation is that this let us take this equation. So our equation says that delta infinity minus delta delta to 1 minus delta 0 times the same for extra minus 1 plus b squared times this expression. I hope that I did not make any mistake in the process of computation. So these formulas are definitely correct. And the formulas for dimensions should also be correct. So I hope it should be fine. 2 delta 0 plus delta 2 1 minus delta minus delta infinity. So this should be equal to 0. So you see, originally we had an equation that delta infinity should equal to delta 0, and now we have some quadratic equation on delta infinity, or equivalently quadratic equation on delta 0. It tells us that once delta 0 is fixed, delta infinity should have two values. Or vice versa, once delta infinity is fixed, delta 0 should have two values. Actually, a little bit afraid of this factor of 2, but maybe it's fine. So So one way, of course, is to solve this quadratic equation and then use this parameterization and guess something. But it's better not to do this because oh, I remember how kind of 5 people were sitting in one room for 3 hours and tried to solve this quadratic equation and simplify the answer, and they failed to do this. I was one of them. So maybe it's better to substitute the answer and check that it is actually this equation is actually satisfied. Oh, by the way, I forgot to make one trivial statement that you see when we insert identity operator in one of the points, so the operator which is killed by L minus 1, this three-point conformal blocks turn into 2-point conformal blocks, and 4-point conformal blocks turn into 3-point, and the dimension drops from infinity to 1. So even for the 4-point case. And we will see the same phenomenon for the degenerate vector. So let me erase all this.
Simple function. and then I'm able to, like, if I choose one of the fields inside to be any possible of the generic field at any level, then I'm able to completely determine it or something.
No, you you will know that it satisfies some equation, and that's all.
But if I have an infinite list of those, I'm not able to completely fix it.
What do you mean?
Because can I have contemporary, like, the degenerate fields at any level?
Yes.
Okay, so if I do this reduction of the endpoint function, inserting every possible degenerate field.
No, no, I don't understand. So there's an endpoint function,
Yes.
right? So are these fields the generic ones or not?
All besides one. Okay.
Yes.
Now I choose that one. Like I will have an infinite list of all these, each of which.
Why infinite?
Because like that one that I choose, like I choose like the general field in the first level, then I choose the general field in the second level.
But it will be oh, so no, for example, for this identity operator, what can you get?
No,
There's
the identity operator is just the first degenerate field, no?
yes.
Now I can do the same for the degenerate field in the second level.
You mean the field with such dimension that it has the singular vector on the second level?
Yes.
Yes.
And then I will do this for the third level and for every level.
You will have some set of correlators with different fields in this point, but they are not related. So each of them will satisfy some equations, but.
Okay, I'm not able to because every operator yourself is different. Yeah, sure. No, that I understood. Yeah, but I thought there were some relation among them for some reason.
No, the only relation that you can glue several fields of this kind and get a higher and get higher degenerate fields, but it's a different procedure. It's.
But I mean, in principle, like once I have a degenerate field, it's also going to generate other degenerate fields, no? In some independent way, no?
From what?
Like I imagine that I have my Verma module, and then I have another point inside my corner, which is giving me a shadow in the middle.
But the only meaningful equation is that corresponding to the highest vector itself. So.
I mean that all the other are in some sense dependent from the first one.
Yes. So.
Okay.
Okay, so there's this equation, and the product of the answer is the following: that if delta 0 is a delta of alpha, which is alpha times q minus alpha, then delta infinity should be equal delta of alpha plus minus, so it's to 1, so plus minus b over 2. And let us check that it actually holds. So delta of alpha plus minus b over 2 minus delta of minus b over 2 minus delta of alpha times delta of alpha plus minus b over 2 minus delta of minus b over 2 minus delta of alpha plus b squared delta of alpha 2 delta of alpha plus delta of minus b over 2 minus delta of alpha plus minus b over 2 what equals to what? So here we can so here we have a kind of a quadratic part and linear part, and maybe it's better to separate them. So quadratic part is minus so a minus square of this number minus plus squares of summons. So it is minus alpha, it is minus plus alpha b. And then there is q times this minus this plus this plus q plus minus b over 2 plus b over 2. Oh, and I forgot to subtract 1 here. On this one, and here we have the same, minus plus alpha b plus q plus minus b over 2 plus b over 2 minus 1. 9 plus b squared the so here we have 2q alpha minus 2 alpha squared plus minus q b over 2 plus minus square root of 4 oh minus So something like this. So now let us collect all these terms together. So we can write it as alpha b minus plus plus q minus b over 2 minus plus b over 2 this one. So and here we have minus alpha squared from these terms. So and now maybe it's easier to check this separately for the lower sign and for the upper one. Or maybe yeah. So for the maybe for the lower sign first. So here this cancels, and we see that it is alpha b times alpha b plus 1 plus b squared minus alpha squared plus alpha b inverse minus 1/2 b squared plus 1, and it's not 0 because there was some mistake. But
is it necessary to do all this computation? Or?
maybe no, but I hope that uh, that
Trust that is the correct
mhm, but it's pity because it is almost correct formula, so it's unclear what what happened. Mm. So probably no. Here the couldn't be any mistake. So let us briefly look at this computation. Ah, so probably I see one mistake because no, it's not mistake. One mistake is here because no, it's again not a mistake. So oh, so somehow I failed to do this computation, mm, but no. So at least the main part of mistake was just because I missed 1 and minus 1. No, it is plus. No, maybe it's something stupid, and maybe it's easier to substitute it into Mathematica to check that answer this one. Oh, so sorry. Uh, but once we now we see what happens. So these fields correspond to different dimensions at infinity, and because of course we have the symmetry that delta of alpha is the same as delta of q minus alpha, but but uh, but it's not that symmetry. These two solutions are correspond to different dimensions. Uh, so in this way, we see that now in the space of conformal blocks with so in the space of this 3-point conformal blocks with uh, delta with alpha to 1, and so alpha plus minus b over 2. And so the space of such conformal blocks is one-dimensional. Otherwise, it is zero-dimensional. But if this happens with 3-point conformal blocks, then we can expect something for the 4-point conformal blocks. Namely, and by the way, another notation for this degenerate field is this one. It is drawn as a very thin tube. This is one way to draw it, like alpha to 1, or it can also be drawn as just a probe, like this. And the meaning of this is that it is something small which does not affect conformal block too much. It is a little bit similar to the identity operator. Because let us look at the case of 4-point conformal blocks. So let us consider such conformal block in the space of such conformal blocks. Here we have this degenerate field. It's some alpha 0, alpha 1, alpha infinity, and here we have alpha to 1. So the question is, what is the dimension of such conformal blocks? What do you think? No, because we can use that basis of conformal blocks. For example, we can cut it here, and we see that it can be some linear combination of conformal blocks with so so. So, so the intermediate dimension here can be either so this alpha intermediate can be either alpha infinity plus b over 2 or minus b over 2. And so dimension of this space of on the space of such conformal blocks is 2. So one conformal block is this one. So if we don't want to draw this pieces of sphere, we can draw it like this. It's another notation for degenerate field. And here we have alpha infinity plus minus b over 2. So plus b over 2 and minus b over 2.
Here we have just one free parameter basically.
What do you call by free parameter? So actually, so there are 7 7 minutes left. Maybe it's enough time to derive a BPZ equation in presence of this degenerate field phi phi 1 2. So maybe I can erase this failed computation, or maybe this correct one. No, maybe better to erase this. BPZ обернув альфове змовочкове equation. For phi to 1. So we take this final vector condition and write that L minus 2 plus B minus 2 L L minus 1 squared acting on phi to 1 is 0. It is the same as to write as before, that b minus 2 dz squared pi to 1 plus integral of dw over 2 pi I w minus z t of z phi to 1 is equal to 0, right? And if you now if you now insert it under the correlator and move the integral with the linear momentum tensor to all other fields, we will get the following equation: b minus 2 dz squared phi to 1 of the later with phi to 1 of z O1 of z1 OK of zk, and this equals to the sum of contour integrals in the case dw phi to 1 of z t of w, and at this moment I can use the I can write the OP of an argument tensor with this primary fields call 1, and here it is delta k o k or w minus zk squared plus d k o k over z minus zk times and let us take n fields on over here we still have a w minus z. So we should take this residues at points zk's. Those are residues in w. So it 2 pi I. So So when we take a residue of this term, we need to take the derivative of 1 over z minus w, and it will give us minus delta k over z k minus over z minus zk squared, right? And the second term is when we substitute here w equals sorry, it should have been w. And here we substitute w equals to zk. So we should also write it with a minus sign, minus d over minus 1 over z minus zk d over d zk. Phi to 1 of z O1 and so On, right?
like when we have the integral representation of the derivative, we get then like a correction with a factorial or something like this.
No, why? We should expand this. But factorial of 1 is 1. Like, so we expand the function as Taylor series around w equals to zk, and if there is second order proof, we only need the first derivative. If it's third order proof, we need 1/2 of second derivative, and so on. Is it fine? So we can now rewrite it once again. We have this equation. So b minus 2 dz squared plus sum of delta k's over z minus zk squared plus d over plus 1 over z minus zk d over dz k acting on phi to 1 of z o 1 of z1 so on o n of zn equals to 0. This is called BPZ equation. So, and what are the consequences of this equation? So we know that in the space of 4-point conformal blocks with one degenerate field, and with this condition is two-dimensional. And we may ask, what are the precise expressions for these conformal blocks? So, so if n equals to 3, then we know that this correlator phi to 1 of z o 1 of z1 or 2 of z2 o 3 of z3 is actually a function of the anharmonic ratio of this z. Well, it's equal to some power to something explicit of z1 of z1 z2 z3 times some function of z minus z1 z 2 minus z3 z no, consensus is stupid. So yeah, this one should be correct. It's now invariant under the inversion of all. So it's definitely translation invariant, scale invariant, and it should also be invariant under the inversion. So that one, no, then it will cancel. So there are several cross ratios, and this one is adjusted such that if z1 is 0, then it is z minus 0 over z minus, so this is infinity, and here it is 1 minus infinity, 1 minus 0. So in this case, it will equal to z, and this cancels. So it's this function of this cross ratio, and if we substitute it into the BPZ equation, we will get some equation like dt squared times f plus something dtf of t plus something f of t equals to 0. So we will get something like this.
Rational function.
Oh, what do you mean?
Like the stuff before it.
Yes, it can be recovered from the from conformal invariance. We basically need to take this dz I dzj over z I minus minus zj squared. Like if you say that z equals to 0, then we should multiply such terms, some Cij, such that the power of any dz equals to corresponding dimension. Maybe it's not so hard to write such an expression. So so we can say that like d dz to 1 so this product times this correlator is invariant, and we want to invariant under at least the global transformations, and we need to construct some object such that this correlator will be invariant, and so that we get a function invariant under the global conformal transformations. So and this function can be constructed like this. So maybe the stupid, the most stupid option is to say that we take dz over dz1 over z minus z1 to power delta to 1, and then dz1 dz2 over z squared delta to 1 1/2 of delta to 1 z1 minus z2 squared dz2 dz3 over z1 minus z2 minus z3 squared dz1 dz3 over z1 minus z3 squared. And here, so it will be delta 1 minus 1/2 of delta to 1 minus delta plus delta 2 minus delta 3 over 2. Here it will be delta 2 plus delta 3 minus delta 1 plus 1/2 of delta to 1 over 2. Here it will be delta 1 minus 1/2 of delta to 1 plus delta 3 minus delta 2 over 2. So if you now multiply, no, why did I put here 1/2? No, it should not be this 1/2. Yeah, so if we so we can check that this ratio will cancel powers of dz, right? And the subject is itself invariant under the global conformal transformations. This ratio will be invariant under this global conformal transformations, and therefore it should be equal to this function of z minus z1, z minus z3, z2 minus z3, z2 minus z1, right? Mm. Yeah, actually, so under this equation, so there is a quadratic equation which has solutions with powerful behavior. So what can this be then other than from hypergeometric hypergeometric equation for f21 and. Hmm. But it's actually better to find these formulas in terms of hypergeometric functions without writing this BPZ equation, because you see it is some super cumbersome computation, and the only thing that we get as a result is some hypergeometric function which depends on three numbers and multiplied by some z to some power and z minus 1 to some power. So it is always better to recover this formula for the hypergeometric function by looking at the asymptotics of conformal block, by looking at its monotomies, and so better not to do this. Especially in the W algebra case. Because, uh, okay, so thanks for your attention.